Welcome back, it's Mr. Veve. This is Unit 2, Part 2. We're on now Module 6, Energy and the Electromagnetic Spectrum. So we're going to start off by talking about UV light and skin cancer. Now UV is ultraviolet, and it's been associated with skin cancer. Now violet light doesn't cause skin cancer, and it's actually part of the visible spectrum. But ultraviolet radiation has a higher frequency than violet light. Therefore, those photons actually have a lot more energy and therefore are capable of causing damage to the skin. Very interesting stuff. So we can look here at the electromagnetic spectrum again. Got a lot more stuff here now. But as you can see, as we move from left to right to the different types of electromagnetic radiation, you get higher and higher energy. Radio waves at the far left being the lowest energy, all the way up to gamma radiation being the highest energy. So you can see ultraviolet there, which is the next step up after the visible spectrum. It's a really cool chart here. You should check it out. So let's move into Planck's law. So Max Planck was a really cool guy. He determined in 1900 that there was a mathematical relationship between the energy and the frequency of radiation. So he found that as frequency increased, the energy of a wave actually increased as well. So he has this equation here, energy equals H, which is called Planck's constant, times frequency. So there you can see it right there. He came up with a constant. So energy is equal to his constant times frequency. And Planck's constant, as you can see there, is 6.63 times 10 to the negative 34 joule seconds. So that is a constant, meaning it never changes. We'll be using that in all of our calculations. So let's do some calculations here. If the wavelength of green light is 5.21 times 10 to the negative 7 meters, what is the energy of this light? Well, first thing we have to do if we want to know energy is we have to calculate frequency. And we are given wavelength, so from the previous module you should remember how to calculate frequency. We do speed of light, 3 times 10 to the 8th meters per second, equals frequency times the wavelength that they give us here, which is 5.21 times 10 to the negative 7. Okay, you're going to rearrange the equation to solve for frequency, and you end up getting a frequency of 5.76 times 10 to the 14th hertz. Now, they asked us for the energy. That is the frequency. We are not done yet. We need to do one more step. We need to plug that into our new equation, which we know is energy equals H, which is Planck's constant, times F, which is frequency. So our energy is equal to that Planck's constant, 6.63 times 10 to the negative 34th, multiplied by the frequency you just got from that answer, 5.76 times 10 to the 14. And you find that is equal to 3.82 times 10 to the negative 19th joules. That is the unit we are using for energy. So make sure you get all of these on the calculations before moving on with this presentation. Okay, great. So Planck's law equation with speed of light right here. So you've got both equations, E equals HF and C equals F lambda. The speed of light equation, if you actually rearrange it to solve for frequency, you get frequency equals speed of light divided by wavelength. So what you can do is if you replace frequency in the Planck's law equation, you can make it so that you don't have to have frequency to solve for energy. So E equals HF, you replace frequency with C over lambda, and you actually get E equals H times C over lambda. That reads energy equals Planck's constant times the speed of light divided by wavelength. That's just a way to rearrange the equation so that you don't have to use frequency. That would have made the previous problem a little bit easier. So let's talk about the implication of Planck's law and the Bohr model. So we know that electrons exist in fixed energy levels with a specific amount of energy, but to move an electron to a higher energy level, you have to excite that electron. So energy must be absorbed to move the electron, and that energy is called the excitation energy. Okay, the amount of energy that you need to excite an electron is actually a fixed amount of energy that is equal to the difference in the energy associated with the level the electron is moving from to the energy that is associated with the electron, the level the electron is moving to. Okay, so that is the excitation energy. When the excitation energy is removed, the electron will return back where it came from, and then that will accompany a release of energy that is equal to that excitation energy. So the energy you put in to excite the electron to move up is the same that the amount of the energy that is released when it returns back to its normal state, its ground state. And this energy is usually released as light, like we talked about the flame tests several modules ago, how different elements will give off different colors of light. So every element has a unique spectra of light, and you can usually identify the element based on what color light it gives off when this excitation happens. So you can see here's a ground state, and there's a few different colors of excited states of electrons that you might actually see. Here's your key term for this module. Hope you guys enjoyed it. Let's move on to the next one.